Hello students, welcome back to the another session of our data structure journey. In this video, we are going to cover AVL tree. AVL tree is also called as the Adelson-Velsky lattice tree. Reason is that this tree is introduced by the two person. That first one is the GM Adelson-Velsky and second one is the EM lattice. So by their two name, the name that is the AVL tree is came up and it developed in the 1962. So here what happened, we can say a tree or a binary search tree can be said as a AVL tree if it is a balanced. So AVL tree is a height balanced binary search tree. That means that AVL tree is also binary tree, but it is a balance. Next question, what is a balance? Balance means if every node has the balancing factor is -1, 0 or +1. Next question, what is a balancing factor? Balancing factor means here what happened in case of tree, node store some information. Here one extra information is added that is called as the balancing factor. So balancing factor is the height of left subtree minus height of right subtree. Next question, what is a height? Height of a tree is the number of edges in a tree from the root to the deepest node. This is the height of a tree. But here what happened? We have to calculate the height of subtree minus height of right subtree. Whatever value, it is called as the balancing factor. So what we concluded right now that a binary tree is said to be a balanced or AVL tree if the height of left subtree and height of right subtree differ by either 1, -1, 0 or +1. So this is called as the AVL tree. Let's take an example. So this is a AVL tree. Next question, how to know whether it is a AVL tree or not? So we have to first understand whether it is a AVL tree or not. So this is the tree is given, root node is the 25, then 21, 35, 10, 25, 28, then 32, 40, 12, 38, 50. Yes, it is a binary search tree. Next question, whether it is a AVL tree or not. It means that if each and every node has the balancing factor, means balancing factor is -1, +1 or 0. Let's start to calculate. So first we have to calculate this 12. So 12, there is no subtree, so its height is 0. This node has height is 0. Next one is 38. Here 38, what happened? Its balancing factor is 0. There is no left right subtree. Then 50. 50, 0. No right left subtree. Then 40. Here what happened? Left subtree 1, right subtree is 1. 1 minus 1, that is 0. Next one is 32. 32, no children, so it is 0. Then 35. Here, left subtree 1, right subtree 1, 2. So 1 minus 2, this is the -1. Next, this is the root node 1, 2, 3. So left subtree is 3 edges 1, 2, 3. Then right subtree, that the right subtree is 1, 2, 3. So 3 minus 3, that is the 0. Next, 21. Left subtree 1, 2. So 2. Right subtree is only 1 edges. So 2 minus 1. This is the 1. Then 28. This is 0. So now in this tree, all the balancing factor is given 0, 0, 0. This is the -1, 0, +1, 0, 1 and 0. So now what we concluded, every node in this tree is balancing factor either -1, 0 or +1. Hence it is a AVL tree. So now next question, whether all the AVL tree is a binary tree or not, or all the binary tree is a AVL tree. We have to check. Right now it is a AVL tree, but it is a binary search tree also. But we cannot say that every binary tree is a AVL tree. So every AVL tree is a binary search tree. Binary search tree means all the left child of children is less than root and right children is that greater than equal to the root children, parent children. But every binary search tree is not a AVL tree. In AVL tree, after performing operation like insertion and deletion, we need to take the balancing factor of every node in the tree. If every node satisfies the balancing condition, that is -1, +1, 0, then we conclude the operation. Means after observation, the tree is balanced, so we don't have to perform anything or any changes. Otherwise, means if any node does not satisfy the balancing condition or balance condition, then what happened? We need to make the imbalanced tree to balance by performing some rotation, which one is called as the AVL tree is rotation. So rotation is the process of moving nodes either to left or to right to make the tree balanced. To make the tree balanced means all the node has the balancing factor is -1, 0 or +1. In case of AVL tree, there are four type of rotation can be possible. First one is the left to left rotation or right to right rotation, right to left or left to right. So these are the five rotation can be possible in case of AVL tree. So we'll cover one by one. Let's start the first one, that is the left to left rotation. So let's take an example here. One node is present with the information 1. We first insert the 1, then balancing factor means that the 0 is the, so it is a balanced tree. Then we want to insert the 2. Whenever we insert the 2, the balancing factor of the is the 0 because there is no subtree. Now which one? That is the 1 is right now is -1 because there is no left subtree, right subtree. So 1, 0 minus 1. So it is 1. After the insertion of 2, for example, we want to insert one more node, that is the 3. As it is a binary search tree, so it will start from root, then right, then it will insert into the right position. Now, after insertion, we have to check the balancing factor. In case of AVL tree, after performing any operation, we have to check whether every node satisfies the condition or not. Means -1, 0 or +1. If it is satisfied the condition, then only we say it is a AVL tree or balance tree. Otherwise, we have perform rotation to make it balance. So now the node 3 is inserted, information 3 we inserted. Now we have to check. So root node, that is the 1, then 2, then 3. So 3 is a leaf node, so its balancing factor is 0. Now we have to calculate 2 because here there is no thing. 1 minus 0 minus 1, so it is -1. Next one is the we have to calculate this root node. There is no left subtree, 0 minus minus so 2. So 0 minus 2. So the what is the balancing factor? Balancing factor is 0. Now after insertion of 3, what happened? Right now tree is not balanced. Before that the tree was balanced. But after insertion of 3, the tree is not balanced. Next question, what happened? We have to balance it. Now tree is imbalanced, so we have balance. Next question, how to balance? Here if we make some rotation, means we shift this 1 to this position, then we shift 2 to this position, then 3 to this position. Means all the nodes shifted into one position left side. Then we got a this one. So now you just analysis. If I move this one, A to this one, so this is the one position, 2 to this position. Now 2 shifted to the root position, then 3 is moved to this one. So here what happened? All the nodes shifted into one position. After shifting, then what happened? We have check whether it is a balanced or not. So here all the nodes, sir, there is no children, 0, no children, 0. 2, 1 minus 1, 0. So all the node has the balancing factor is 0. So it is a balanced. So it is a balanced tree. After the LL rotation, the tree is right now balanced. So what we concluded that in LL rotation, every node shifted from one position left to the current position. So one position. So this is shifted one position. This shifted only one position. This shifted also one position. That's why every node shifted one position left from its current position. Now let us understand the RR rotation. In case of RR rotation, every node moves from one position right to the current position. Let us take an example. First node element is that is 3 we are inserted. Right now we have to calculate the balance factor. There is no left right subtree right now. So the root node that is the 3, the balancing factor is 0. Now we insert the value 2. 2 is less than 3, that's why it will be inserted into the left side, that is the after insertion we have to calculate the balancing factor. So here balancing factor is 0. There is no left subtree, right subtree, so it is 0. Now the 3 balancing factor is changed to 1 because the balancing factor is left height of left subtree is 1, right subtree is 0. So 1 minus 0, this is the 1. For example, after that we want to insert the value 1. So after that what happened? Binary search is a 3, then 2, then 1. After insertion of this value, so we have to check what is the balancing factor. Balancing factor of the 1 is 0, left and minus right subtree is 0. Then balancing factor of 2 is that is the height of left subtree is 1, height of the right subtree is 0. 1 minus 0, that is 1. Then height of the left subtree 1, 2. Here it is 0. 2 minus 0. So it is 2. So balancing factor is of 3 is 0. Right now what happened? It is not a AVL tree. Reason is that balancing factor can be minus 1, 0 or plus 1. Now it deviates the condition. So it is a imbalance. So now our tree is imbalanced. Next question. How to make it? We have to perform some rotation. So here what happened? We have to perform the right rotation. So this node moves to this location, 3 moves to this location, 2 moves to the 3 location, 1 moves to the 2 location. So that's why it is called right to right. After perform RR rotation, this is the outcome, and all the node has the balance factor 0. So it is a balanced tree. So what we concluded, in case of RR rotation, every node shifts from one position to the right of current position. So next type of rotation is the LR rotation, left-right rotation. So here it performs a sequence of single left rotation followed by the single right rotation. Let us take an example. For example, first we insert the value that is the 3. So it is a root node right now. Its balancing factor height is 1. Then we want to insert one value, 1 means is less than 3, so it will come to the left side and it is inserted here. So after insertion of this node, we have to check the balancing factor. Balancing factor of the 1 is 0 because there is no left right subtree. Then we have to check. Here 3, in case of 3, what happened? Left subtree is 1, right subtree is 0. 1 minus 0, it is 1. Next node we want to insert, that is the 2. 2 is less than 3, so it comes to the left hand side. After that it is greater than the 2, 1 value, so it will come to the right hand side. Once it is inserted, after that, as it is a AVL tree, we have to check each and every node balancing factor. 2, 0 because there is no left right subtree. Then 1, 1, there is left subtree is 0, 0 minus 1, so it is minus 1. For 3 it is 1, 2, so it is minus 2. Sorry, it is plus 2 because it is left subtree. So left subtree 2, my right side is the 0. So 2 minus 0, it is 2. So here right now it is not a balanced tree. So it is not a balanced tree because balancing factor of 3 is 2. Next thing we have to think how to perform rotation so that we can get a desired result. Just you have to think after insertion of this node, the tree becomes imbalanced. So then we have to check which sequence the insertion is done. Insertion is done on the left and right. So according to that, you have to decide which type of rotation you have to do. So now we have to perform the left rotation. So this one is the left rotation, means two shift to the one position, one shift to the another left position. So after LL rotation, the tree looks like this. But it is not balanced because here this is the 0, this is the -1, this is 1, this is 2. So it is imbalanced. So again we have to make the right rotation, first rotation right, then second rotation. So after performing this operation, we will got the tree. Now we have to check whether it is a balance or not. So we have to check the balancing factor. Each and every node is comes under the -1, 1 and 0 balancing factor because all are 0. So it is a balanced tree. So after LR rotation, the tree is right now balanced. So we first perform the left rotation, LR rotation, then we perform RR rotation. So combinedly it is called as the LR rotation. So in RR rotation, there is a sequence of single left rotation followed by the single right rotation. So single left we perform and then we perform the single right. Next one is the right left rotation. So here what happened? There is a sequence of single right rotation followed by a single left rotation. Let's understand how it's possible. So for example, element 1 is present. After that, we want to insert another value, that is 3. When the insertion sequence is first 1, then 3 we want to insert whenever 1. That is the balance factor is 0. So it is balanced. But after insertion of 3, we have to check the balance factor. So it is 0. 1 right now, height of left subtree minus height of right subtree. 0 -1, so it is -1. After that, we want to insert 2. 2 means more than the 1, so it will come to the right side. After 3, it is less than the 3, so that's why it comes to the left side. Now, after insertion, what happened? As it is a AVL tree or height balance tree, we have to check the balance factor. Balance factor for the node 2 is 0 because there is a leaf node. Then we have to calculate this one. 3. For 3, left subtree is 1, right subtree height 0. 1 minus 0, it is 1. So here what happened? It is left subtree is 0, right is 2. So 1 minus 2. Now it is 2. So now what happened? Now the tree is imbalanced. So now our tree is imbalanced. So if it is imbalanced, then what happened? We have to do the rotation. Next question, how to do it? So at that time you have to check. After insertion of 2, the tree becomes to imbalance. So after insertion means you have to check the sequence. Now this is the right, then this is the left. So first right node is inserted, after that left node is inserted, after that the tree is imbalanced. So which rotation we have to follow use? We have to use the right and left. How to do it? So this one is for right rotation. So this is also right rotation. So node go to this one. So this is the RR rotation we have to perform. After RR rotation, the tree becomes like that. It will move to the 3. After RR rotation, if we check the balance factor root node 3, so it is -1, left subtree is 0, 0 -1 it is. So now for 1, balance factor is height of left subtree minus height of right side. Left subtree is 0, right is 2. So 1 minus 2. 0 minus 2, so it is 0. Anyhow, we know it is a right left means first we have to perform right rotation, then we have to perform left rotation. So left rotation means this way it will move. After that, this one is move. After that, we got this. Now we have to calculate the balance factor. 3 is 0, it's a leaf node. It is also 0. It is also 0. So this is not minus 0, this is 0. So what we conclude that? We conclude that in case of RL rotation, there is a sequence of single RR rotation followed by the single LL rotation. So what are the operation available in the AVL tree? So there are three types of operation we can perform: searching an element present inside the AVL tree or not, how to insert the data into the AVL tree, and how to delete the data into the AVL tree. So first we have to cover what is a search operation. Search operation means we are searching an element present inside the AVL tree or not. In AVL tree, the search operation performed with the time complexity order of log n. The search operation is similar to the search operation in the binary search tree. Because we know AVL tree is a binary search tree, added with the condition is that it should be balanced, means each and every node should have the balance factor, that is the 0, -1, +1. So here what happened whenever we searching an element, so it is same as the binary search tree. So this is the algorithm we have to follow. Read the search element from the compare the value with the root value. If both the value match, then it is that type. Otherwise, we have to check whether it is smaller or larger. For example, we want to search the element 32. So as 32 means we have to start searching from the root node. Root node is the 25. Then we have to check 32 is less than or greater than. So it is greater than 25. So it will go to the right subtree. After that, we reach here. So right now 32. So then we have to compare 35 is equal to 32. 35 equal to 32 or not? No, it is not equal to 32. Then what happened? We have to go to the less than. So it will go to the left subtree and we got the value. So this is the same way we are searching the element present inside the binary search. Next, we have to know what perform insertion operation in a AVL tree. In case of height balance tree, the insertion operation performed with the time complexity order of log n. Let us understand what is the algorithm. The insertion operation of an AVL tree or height balance tree is similar to the insertion operation in binary search tree with added features. That added features is for the balancing factor. After insertion, we have to check the balance factor of each and every node. If the balance factor of each node is -1 or 0 or 1, then what happened? Then the tree is balanced, so it can go for the next operation. If any single load balance factor is other than the -1, 0 or +1, then we have to perform the suitable rotation to make the tree to balance. After balance the tree, we can go for the next operation. This is the difference between insertion in the binary search tree, AVL tree. Both are same, except that in case of AVL tree, as it is a height balance tree, after insertion each and every node, we have to check the balance factor. If it is not -1, 0 or 1, then we have to go for RL rotation or LR rotation or LL rotation, RR rotation. There are four category of rotation we are just covered. So according to that, we have to make the rotation and make the tree to the balance tree. Next one, how to perform or algorithm to the delete the AVL tree. The deletion operation in the AVL tree is similar to the delete operation in the binary set. After deletion, we have to check the balance factor of each node. If it is -1, 0 or +1, then we have to go for next operation, means tree is balanced. We don't have to do anything. We go for whatever next operation for the tree, we have to use it. If any single load balance factor is other than the -1, 0 or +1, then we have to perform suitable rotation. Suitable rotation means either we can go for LL rotation, RR rotation, RL rotation, or LR rotation. Any four category we can go and make the tree to balance. And after that, we can go for the next operation. So this is all about the AVL tree we covered today. Hope you are able to understand the concept of the AVL tree. Thanks for watching the video. Please subscribe the channel, like the channel, share the channel. Thank you so much.